So we're going to do the first application of iterated integrals, in particular double integrals, and we're going to do this to find areas between two curves. And well, this is something that we actually did back in Calc 1, finding areas not just under the curve, but actually between two curves. But this time we're going to define this using a double integral. So how are we gonna go about this? Well, so number one, so back when we defined the area under the curve, that was to to find infinitely many areas under rectangles. However, this time, since this is basically a rectangular, so to speak, region, so we're going to take a sample, a rectangular sample, and in this case this rectangular sample will have some delta x and delta y. Alright, so that the area of that sample is simply length times width, which is just delta x delta y. Alright, and in this case, well, we can define these regions into essentially two different directions. So let's do the same over here. For another sample, that's also delta x, that's also delta y, the x component and the y component respectively. Well, it turns out that we can define the regions in two different ways. Right, number one, a region is vertically simple if, for example, if we want to trace vertical lines, notice in this case every time I do this vertical lines, the top function g2 is always at the top of g1. That's what we call a vertically simple region. And in this case, whenever we want to do this vertically simple region, we are going to integrate in the following order, in the order dy and then dx. So vertically simple. However, on the other hand, if we think of functions of y sideways this time, if in this case h2 is always to the right of h1, when I trace these lines right here, notice how it's always the case, then this region, it's called horizontally simple. And we'll get an M here. Alright, so in the end, we're going to have the following integral. Regardless of the order, the area will be the double integral over some region R, that's like the subscript of the two integral symbols, and of dA. And in this case, depending on the case, dA could be either dy and then dx, or dx and then dy. In some cases, the order won't matter as well. So we will look at a couple of examples in how, so we can see in which cases it's better to treat the problem or treat the situation as a vertically simple or horizontally simple. In fact, for some of them, we're going to do both just to verify that indeed we should get the same result regardless of the order that you take. Alright, so let's look at one example. So let's write an iterated integral to find the area of the rectangle formed by the lines x equals to 1, x equals to 4, y equals to 2, and y equals to 6. Alright, Cartesian plane, and well, x equals to 1 and y equals to 6. 1, 2, 3, 4, 5, 6. So x equals to 1, x equals to 4, and y equals to 2 and y equals to 6. So we are going to find the area of that rectangle. Do we really need a double integral to find the area of this integral? How about we just use 4 times, what's this? 3 times 4. Alright, that's just going to be 12. But yes, we're going to do it. We're going to set up a double integral to, in this case, find this area. Well, number one, let's determine whether this region is vertically simple, horizontally simple, or even both. Well, if we try these vertical lines, notice y equals to 6 is always at the top of y equals to 2. So indeed, this region is vertically simple. On the other hand, let's see if the other test works. So in this case, for horizontally simple, is x equals to 4 always to the right of x equals to 1? It is, right? In some cases, it won't be the case. So that's how we know in this case in this case we can go either way. So let's go about vertically simple. So in this case, we're going to pick vertical strips to define this region. So let's go vertically simple. So in this case, area is going to be the integral, the double integral over the region times of the a. And by the way, for a double integral to represent area, there has to be nothing between the integral symbols and the dA other than an invisible one. If you see something like a 5, an x squared, sine of x cubed, whatever, that's no longer an integral representing area. In that case, that's an integral representing volume, which we're going to look at next. All right. So it has to be a 1 to represent area. So in this case, since we chose to go about vertically simple, so that's going to be the y first and then the x. So let's look at the limits of integration first with respect to y. All right. In the y direction, we're going to go 6 and 2. So we're going to go from 2 to 6. And in the x direction, we're going to go from 1 to 4. So let's evaluate this integral, see what we get. Well, number one, the integral of the y will be simply y from 2 to 6 dx, and don't forget the limits of integration for the first integral. Well, so that's going to be the integral from 1 to 4, that's 6 minus 2 dx, and that's going to be the integral of 4 dx from 1 to 4. Integrating 4 dx, isn't that just going to be 4x from 1 to 4? And 4 times 4 minus 1, which is 4 times 3, which equals 12, as expected. I know we could have just used the length times width formula. Yeah, 4 times 3, that's 12. But now it's important to look at this example so we can see what's going to happen for the next exercise. All right. For example, number 7, they're asking us to use an iterated integral to find the area enclosed by y equals to 4 minus x squared and y equals x plus 2. So that actually looks like a Calc 1 problem, right? I mean, it doesn't look any different than a Calc 1 problem. But the way we're going to set it up, well, number 1, graph. Let's get the graph. And well, so what do we have? Y equals to 4 minus x squared. That's a parabola shifted up 4 units and opening down because of the negative sign in front of the leading coefficient, right? From the x squared. So That's 1, 2, 3, 2, 3, and 1, 2, 3, 4, 5. So it's a parabola 4 units up and having x-intercepts at plus and minus 2. And it's upside down. And we also have the line y equals x plus 2, which is a straight line with a y-intercept at 2 and a rise over run of 1. So I'm going to go like this, basically. So that's the region of integration. All right. Let's have a look at this problem, this graph, and determine whether we have a vertically simple, horizontally simple, or both. So number one, let's make the test for vertically simple. So if I pick vertical strips, the parabola, it's always at the top of the line, right? Do you see a point for which it's not the case? Well, at least in the points of intersection. So for this region, it's vertically simple. Now, let's check if it is horizontally simple. Well, for this part right here, the rightmost part is part of the parabola, and the leftmost part, it's still itself the parabola. Same over here. Same over here. However, what happens here? Now the rightmost is the diagonal line, and the leftmost is the parabola. So in this case, for this reason, because it's not always the case that the same function, that one function is the rightmost and the other one is the leftmost. Like in this case, we have part of the parabola and part of the line, so it's not horizontally simple. So in this case, to make the problem a lot easier, we will have to go about vertically simple, because otherwise, I mean, you can still do it in the horizontal direction, that is using functions of x. However, you might remember this situation in Calc 1 when you had this. You had to calculate area 1 and area 2. You had to set up two different integrals. Remember that from Calc 1? Well, so in this case, now that we have more reinforced tools about looking at regions, well, so we can now decide which order to go. In this case, let's go about vertically simple. All right? Okay, so that is, we're going to integrate to vertical. That is dA equals dy and then dx. If it were on the other hand, horizontally simple, we would have gone the order dx and then dy. Alright, so let's find the integrals in this case. Well, so let's find the integral. So that's the double integral. I'm going to leave some space for something here. So that's the integral of dy dx. Well, the limits for the innermost integral are going to be whatever lies above and minus whatever lies below for the upper limit and for the lower limit respectively. And again, if we do these vertical strips here, so that's the top, the bottom will be the line, which is x plus 2, and the top will be 4 minus x squared. So that's the part of the integral in which we're going to define the vertical direction. Now for the dx, those are going to be the limits of integration in the x direction, and that's going to be actually finding the points of intersection here. So in this case, to get those points of intersection, we would need to set these two equations equal to one another. That is, 4 minus x squared equals to x plus 2. And that is, if we solve this equation, that's a 0 equals x squared plus x, and 2 minus 4, that's negative 2. And we can factor this trinomial using the double bubble method in this case because the leading coefficient is 1. If we had a leading coefficient different than 1, then we would need to go about a different method. So we were looking for factors of negative 2 that add up to 1, and I think, how about plus 2 and negative 1? So that means x equals negative 2 and x equals 1. Well, I think this checks with the graph that I did before, right? So those are going to be the limits. That's going to go from negative 2 to 1, and we're good to go about the integral. Alright, so the integral of the y, that's simply going to be, okay, the integral from negative 2 to 1, that's a y, evaluated from x plus 2 to 4 minus x squared dx. And then substituting upper limit minus lower limit, that means 4 minus x squared minus x plus 2 dx. Alright? Alright, hold on. So again, doesn't that look like those Calc 1 integrals that we did to find areas between curves? This is the upper minus lower. So, well, back in Calc 1, most likely they told you, oh, okay, just do the upper minus lower or top minus bottom. Well, where are these coming from? From defining regions that are vertically simple. When you did the reverse order using functions of y in this case, well, they just told you to go rightmost minus leftmost, but what they didn't tell you is that you were integrating over a horizontally simple region. So now I think after looking at this, it has a better meaning, you know. So let's simplify this integral. So that should be, well, let me go with the quadratic terms first. Negative 2 to 1. And that's a negative x squared minus x. And then 4 minus 2, that's going to be plus 2 with respect to x. So if we integrate, that should give us negative x cubed over 3 minus x squared over 2 plus 2x. Evaluated from negative 2 to 1. And well, for this, just to save some time, I'm just going to give you the result. That should give us 9/2. Right. Ultimately, what we care about is how we set up the integral. How do we go about whether, depending on whether this is vertically simple or horizontally simple. All right. And again, notice how, in this case, what do we have in the integrand? Wasn't that just a 1? All right. So let me go back to the definition in the previous page. To define area, the integrand must be a 1, whether you do it in the x direction or the y direction. Alright, if it's something else than 1, even a 2 or a 5, even a simple number, even 0.00001, that's already volume. It's not anymore area. Which is actually the next topic, finding volume. Alright. So, the way we're gonna go about finding volume is in a very similar way that we define finding the area under the curve. At that time, we found the area under a rectangle, we made it as tiny as possible, and we added infinitely many of them using a Riemann sum. Now we're gonna go about finding volumes of, well, not rectangles, but rectangular prisms in this case. So we're gonna take one sample of this rectangular prism, and well, To find the volume of a rectangular prism is the same as finding the volume of a rectangular box or parallel pipette. That's another name for rectangular box. And we simply go about V equals length times width times height. That's the volume of a box. All right. In this case, well, what do we have for the length times width? So for the length times width, you know, that's like finding the area of the base. So we're going to go about the area of the base first. Well, in this perspective, is this square that I just drew here. I don't think it contrasts very well. Maybe I need a different color for this. Maybe this color, hopefully. Much better. So that's okay. This is the x direction, this is the y direction. So there's a delta x here, there's a delta y in this direction, which is really okay. Length times width, which is dy dx, I mean delta x or delta times delta y or delta y times delta x, doesn't matter. Ultimately, this is our dA, if you will, or let's call it delta A, because that's only an increment. So far, it's only an increment in the area, and that increment as tiny as possible. And then in this case, adding infinitely many of the volumes of these boxes, that's going to give us the volume of this region. All right. So, well, so what's h in this case? H will be. So all we have to do to get the z value, evaluate the function at corresponding x and y, which in this case is simply f of x, y. All right? So here is the thing. In order to find the volume of the kth box, because again, in the same way that we did a partition of an area under the curve by, well, we did it first with 4 rectangles, then 5 rectangles, 25 rectangles, until we get as many rectangles as possible, so we get the actual result. And well, that many rectangles were infinitely many rectangles. In this case, notice this smooth surface is chopped into, or is partitioned rather, into boxes, into rectangular boxes. So the smoother the boxes here, then it will give us the actual volume of the solid. And in this case, how many of these boxes? Well, infinitely many. So we're not going to go through the Riemann sum in this. Instead, here's the formula after, because that'll involve doing a double infinite sum, and that's going to take forever. So ultimately, it's just going to be another double integral. But in this case, whatever we have in the integral, in the integrand rather, it's no longer going to be just the number 1. It's only the number 1 when we're looking for area. When we have something else, that's already volume. All right? And that's the note here actually. If f of x equals 1, we have our integral for area. Right? Okay, so let's have a look at one example. Whenever we have a rectangular region, we have this following theorem, which is called Fubini's theorem, which essentially tells us that we can go about whatever order, either horizontally simple or vertically simple, either way. Okay, so let's see. Sketch the region whose area is given by the iterated integral. Then switch the order of the integration and show that both orders yield the same area. So we're not going to find volume yet. We're going to do that for the next example. So in the meantime, let's look at changing the order of integration, that is essentially using Fubini's theorem to set up the integral both ways. All right. So number 1, it would be a great idea to to set up the integral. But in this case, notice they are not telling us that to find the area between these two curves and blah blah blah. No, they're already telling us, they're already giving us the integral, so we need to break it up into pieces and from there sketch the region. So notice the innermost integral. The innermost integral has an upper limit of 3 and a lower limit of square root of x. So that means that this came from a vertically simple region, which is going to look like this. So that's going to be from the top we're going to have y equals to 3. 1, 2, 3. And from the bottom it's going to be the graph of square root of x. And well, the limits in the x direction are from 0 to 9. That is from 0 and 9, which makes sense because the square root of 9 equals to 3, and that's where the two graphs intersect at. All right. Again, let's make the test to determine whether this region is horizontally simple and vertically simple. So number one, is it vertically simple? All right. Let's see. Top minus bottom, top minus bottom. Are we getting always the same top and the same bottom? That is the horizontal line always at the top of the curve? Yes. So it's so far is vertically simple. What about horizontally simple? Are we always getting the curve to be the rightmost and the y-axis in this case to be the rightmost? So it's both horizontally simple and vertically simple. So that means in this case we can apply Fubini's theorem and represent this integral but in two different ways. So let's go about the first order that we have over here. Number one, we're going to integrate with respect to y and then with respect to x. So that's going to be the order. So 0 to 9, and the integral of dy is just y from root of x to 3 with respect to x. So that's going to be equal to the integral from 0 to 9 of 3 minus root of x with respect to x. So that's the integral. If we want to evaluate the integral of square root of x, we would need to change this, to change it to rational exponent form. So that's going to be the integral from 0 to 9. None more integral. That's actually 3x minus x to the 3 halves over 3 halves, which is 2/3 instead. And let's go from 0 to 9. This means 3 times 9 minus 2/3, and that's 9 to the 3 halves. And minus, do we agree that's going to give us just 0 because 3 times 0 and 2/3, 0 to the 3 halves, that's just a big 0. Well, so that's 3 times 9, which is 27, and well, minus 2/3, that's going to be the square root of 9. In this case, it's a perfect square. I'm going to go about the other property of radicals, quantity, or actually cubed. So that's 27. That's 27 minus, the square root of 9, which is 3. And then 3 cubed, that's 27. But 27 divided by 3, isn't that 9? 9 times 2? 18. And what's 27 minus 18? Isn't that a 9? So that's a 9. Let's go about the other order. So we're going to set up an integral, but now we're going to go dx and then dy. That means we're going to go horizontally simple. In other words, we will define what in Calc 1 or Calc 2 depending, it's going to go rightmost minus leftmost. But in this case, we would need to define this as functions of y. All right? So on the one hand, we're going to have this square root of x. Oh yes. Y equals x on square root of x. Oops. Which is the same as saying x equals y squared. And this vertical line right here is x equals to 0. So we're going to integrate from 0 to y squared. All right. And the limits of integration in the y direction are going to go from y equals to 0 to y equals to 3. And we may go about the integration from 0 to 3. The integral of the x is x, evaluated from 0 to y squared, dy. And the integral from 0 to 3, that's y squared minus 0, dy, which is simply the integral of y squared with respect to y, 0 to 3. And then this is y cubed over 3, evaluated from 0 to 3. So in this case, 3 cubed over 3 minus 0 cubed over 3. So that's 3 cubed, which is 27, over 3. Isn't that a 9? Minus 0, which is simply 9. So we should obtain the same result whether we go vertically simple, horizontally simple. In fact, in some cases, doing it one way or the other might be easier than the other way. All right, and that's also something you analyzed back in Calculus 1 when you were finding areas between two curves, which is really what we're doing, but without even thinking of that vertically simple, horizontally simple. Most likely you got into examples like set up the integral and choose the easiest one to evaluate. All right. So let's go about finding volumes. All right. So find the volume of the solid that lies under the paraboloid z equals f of x, y equals to x squared plus y squared, and above the region in the xy plane enclosed by y equals to 2x and y equals x squared. All right. So this time, our double integral, we will no longer just a 1 in the integrand. It will have something else, which is going to be this f of x, y. So volume, which is the double integral under a region r for the function f of x, y, dA. And well, we may go about dy dx or dx dy. We don't know yet. So that's why initially we go about the dA rather. And well, so let's graph this. So let's graph let's graph this in 2 dimensions. So that's the graph of the parabola and then the graph of the line. All right, both intersecting. So let's see. So in this case, let's set up the integral and decide whether we go about vertically simple or horizontally simple. Well, number one, let's see. Let's answer the question. Is it vertically simple? So is the line always at the top of the parabola, at least for this region that we are bounded by the 2? Okay. Is it horizontally simple? It's also horizontally simple. However, I think this setting is just ready to go about vertically simple, because otherwise we would have to solve x equals 1/2 y and x equals the square root of y. So no need to go about functions of y. So in this case, well, number one, let's have a look at GeoGebra real quick. So in this case, well, so f of x, y is the paraboloid x squared plus y squared dy dx, and then from in the y direction, that's going to be the line minus the parabola x squared x, 2x rather. And in the x direction, the limits of integration are going to be whatever those points of intersection are between these two curves. So let's go ahead and find them. So that's x squared equals 2x. X squared minus 2x equals to 0. We can solve this by factoring polynomials, the GCF in particular. That means x equals to 0 or x equals to 2. Well, which is consistent with what we have in the graph, right? Alright, so let's write down those limits of integration. So that's from 0 to 2. And let's integrate with respect to y. So x squared is held constant, so we're integrating a constant times the integral of the y, which is simply y. So that's from 0 to 2. That's x squared y. And the integral of y squared with respect to y, that's y cubed over 3. And that goes from x squared to x with respect to x for the outermost integral. But again, recall that this time we have a lot of x's and y's going on everywhere. So these limits of integration are going to be plugged in only wherever we see the y, because the first integration we did it with respect to y. We're not just going to plug them in everywhere I mean. So that's the integral from 0 to 2 of x squared times x plus x. Oh, it's 2x. 2x plus 2x cubed over 3 minus x squared times x squared plus x squared cubed over 3 dx. All right. Let's simplify this madness. All right, so that's the integral from 0 to 2. So that's going to be 2x cubed. And that's 8x cubed over 3. Minus x to the 4th. And minus also x squared cubed. Careful, power of another power. What do we do with the powers? Multiply, so that's x to the 6th power, and that's over 3 dx. Let's combine like terms. Let's combine the cubics. So 2 times 3 is 6 plus 8, that's 14. 14 14x cubed over 3 minus x to the 4th and minus x to the 6th over 3 dx. And if we integrate this, we should get, okay, so 14x to the 4th over 4 times 3, which is 12, minus x to the 5th over 5, minus x to the 7 over 7, but times 3, that's a 21. And that goes from 0 to 2. And the usual upper limit minus lower limit, that's going to be, okay, 14 over 2, that should reduce to 7 over 6. X to the 4th minus x to the 5th over 5 minus x to the 7 over 21 from 0 to 2. And that's, okay, 7 over 6 times 2 to the 4th minus 2 to the 5th over 5 minus 2 to the 7th over 21 minus, well, do we agree that if we plug in a 0 to all these three terms, it's just going to go 0? Okay, big 0. And after simplifying this madness, this should be 216 over 35. Right? Let's see what's next. One more of finding volumes under given regions. And for this one, well, we got a picture of it. I think it's easier to see this picture rather than what I wanted to do using Desmos. So what we want to see here is how the intersection of these two planes under the parabolic region. So we have the planes z equals to 1. Okay, what's that plane z equals to 1? So let's get an idea of what that plane is. So it would be this plane, right? Z equals to 1, 2, 3, etc., right? But in this case, this is an inclined plane. So z equals to 2 minus y. In this case, it's this diagonal plane. Okay, let me go with the colors. Let me go with another color. And well, this is another plane, if we will. Alright, so, I still have the planes here. I haven't gotten rid of them. So, it's like having these two intersecting planes. Like this, alright? But then I go about some... Okay. So, what I'm going to do with these planes is cut them in the shape of a parabola. Like this, alright? And I'm going to do the same with this other plane. So we're going to get some scissors or something and cut this plane. So we're really finding the volume of whatever is left when we cut this part, right? So let me see if I can sort of do this well. Sort of. It's not going to go perfectly. But I think you get the picture, right? So now we get this parabolic solid, sort of. Alright? So we can think of just getting a knife or a sword, I don't know, a lightsaber, you name it, and get this. Huh? I know, I should have brought mine, right? My master replica there. And well, so yes, the good thing is we have this solid picture, right? So notice these dashed lines here. The purpose of these dashed lines I did was just to extend the shape of the planes. Ultimately, okay, let's get rid of them. And so here is the thing. It turns out that it's important to analyze what's going on below that surface for which we're finding the volume. Well, they're telling us that x is varying from 0 to 1. And y is varying from 0 to 1 minus x squared. So technically, we should extend this graph along the negative axis, the negative x-axis, and keep going the other side like this. Alright? So this graph I did in red right here is represented in the 2D plane like this. Alright? So if our eye is looking from the top, we should be seeing that upside down parabola. But in this case, well, we only want the part in the first quadrant xy, right? Which would be the first octant in the 3D space, okay? So let's see. Let's set up the integral Let's see, so alright, so number one, volume equals to the double integral over the region R of f of x y dy. Oh, I don't know if it's dy dx. For now, let's call it. We haven't chosen an order yet. However, notice that we already have functions of x. So I think the dy dx order should be fine. So let's call it dA for now. This will be double. That's the plane. Well, for the planes, notice we're going to do exactly the same as we did when we found areas between curves, top minus bottom or rightmost minus leftmost. However, in this case, the situation with the solid, which plane is the top, which plane is the bottom? Isn't it the top one, the one that is as an incline? And then the bottom plane is the one that is horizontal. That is, this is the one below, and this is the one above. All right. So even for solids work like that: higher minus lower, or tall or upper. Or yes, upper minus lower. So that's going to be the taller, which is 2 minus y minus 1 dy dx. And well, the integration in the y direction. So let's go back to our 2D graph right here. Again, this region is of course vertically simple because the parabola is always at the top of the x-axis, right? And it's also horizontally simple because that curve, that parabola, it's always at the right of the y-axis. But this time we're just looking at vertically simple. So for vertically simple, that's going to be the lower limit, which is 0, the upper limit, which is 1 minus x squared, and the limits are going to go from 0 to 1. All right. So let's evaluate the integral. Okay, let me write it more neatly. It looks like a mess. From 0 to 1, from 0 to 1 minus x squared, and that's 2 minus y minus 1. Much better. So let's simplify this first. That's the integral from 0 to 1. The integral from 0 to 1 minus x squared. 2 minus 1, that's 1 minus y. So that's the integral, or negative y plus 1. Well, let's integrate. Yeah, I think we're going to have enough time. So that's the integral from 0 to 1. And that's the integral, that's negative y squared over 2 minus y. And that goes from 0 to 1 minus x squared dx. And then again, upper limit minus lower limit. But well, in this case, it's only one variable, so no issues. So that's integral from 0 to 1. So that's negative 1 minus x squared over 2 minus 1 minus x squared. So that's the first part. Minus, do we agree that if we plug in 0 for both terms, that's going to get zeroed out again? So just go about big 0 dy. No, dx. Alright, so let's simplify this. So that's going to be the integral from 0 to 1 of negative 1/2 1 squared, which is 1 minus 2 times x squared plus x to the 4th. And then minus 1 plus x squared dx. So we're ready to integrate all this with respect to x and find the volume. So let's simplify this. So number one, negative 1/2. Let's distribute this negative 1/2 plus 2x squared times 1/2. That's just x squared, and minus x to the 4th over 2 minus 1 plus x squared. All right, dx. So this will be negative 1/2 plus, or rather minus 1. That's going to be 3/2. And I'm just going to go about negative x to the 4th over 2 plus x squared, and then minus 3/2 dx. And well, so if we compute this integral, we should get 2/5 at the very end, and that's the volume. All right.